In this chapter, we are going to talk about elimination reactions, which are another type of reaction that alkyl halides can undergo. On the first slide here, I have a picture of quinine, and this is the chemical structure of quinine. Now, the synthesis of quinine in 1944 is considered by some chemists to be kind of the start of organic synthesis. It was a treatment for malaria, which is why people were interested in synthesizing it. And I put it here because one step of the synthesis involves the elimination reactions that we're going to talk about today. Now, let's talk about some of the general features of elimination reactions. Elimination reactions, when we discuss these, I'm trying to figure out where I want to put this, they are really used to introduce pi bonds into organic compounds so they can be used to produce alkenes, which are the double bonds, and alkynes, which are the triple bonds. And these have different reactivities as well. Now, elimination reactions involve the loss of elements from the starting material to form a new bond in the products. So when we look at this, right, you're going to notice that there's a B with 2 electrons here. This is just a generic Bronsted-Lowry base. And so this is a way to represent a base generically. I want you to notice that we have our halogen here represented with an X, and we are also going to lose a proton on the carbon adjacent to the halogen. Not the same carbon that's on the halogen, right? But it's got to be the next door neighbor. Okay, so the next door neighbor helps out in this reaction here. And so we eliminate the HX, which in our cases, if it's a halogen, forms an acid. And then we form a new pi bond, which can be a double or triple bond. When you look at these specific examples, I've got specific examples down here. You'll notice that these are double bonds. And these can work with straight chains or cyclic compounds as well. So we don't want to forget our cyclic compounds. I also want to point out that these examples are shown with their cations here, their counter ions, and we can just ignore those when we go through this mechanism, but they do keep the charges balanced over here. Now, removal of this HX is one of the most common methods to introduce a pi bond and prepare an alkene, and this is also called dehydrohalogenation. D a lot of times just means to remove, and then we have hydrohalogenation. So if we're talking about removal, right, and hydro refers to the H, and then halogen refers to one of the halogens, that's where this name comes from. Now, dehydrohalogenation is an example of beta elimination, which is a broader term used to talk about the loss of elements from 2 adjacent atoms. All right. And so in this instance, it's an alpha carbon that's bonded to a halogen and the beta carbon. So when we look at an example of this, we are going to look at the hydrogen, right, on one carbon group, and we're just going to use a generic R to say that's the rest of the molecule. And then a halogen here. And so what happens is that base comes along and it steals that proton. So it's going to take that proton back and it leaves all its electrons behind. So those electrons are going to go right there to form a double bond. Now, when they form that double bond, carbon can only form 4 bonds. So it's going to kick out one of these. because this is the most electronegative atom here, and there's the biggest electronegativity difference, that means these electrons are closer to this electronegative atom, so it's more likely to be this one. So then those electrons go on that halogen. When this occurs, you get the double bond that's formed, and HB, and then you have your leaving group. Now, when we talk about the alpha and beta carbons, the alpha carbon here is the one with the halogen. The beta carbon is the one that is next to the halogen where the base removes the proton. Okay, and so this is the alpha and this is the beta. And so when we come over here, this would be the alpha and this would be the beta. And that's what we would see with that new pi bond that's formed. Now, the most common bases that are used for this reaction are shown here. So don't memorize these, but it is good to recognize which ones are bases. We're all probably pretty familiar with OH minus as a base, but you know, it's always good to kind of review the tert butoxide because that's probably a new one that you haven't seen before. It's been a while since you've seen. So let's look at an example where we have to predict the products. So when we're here and we're going to draw kind of the products of a dehydrohalogenation, let's say that we are trying to predict the product right, when this molecule undergoes dehydrohalogenation. And so we're going to say, all right, look, this molecule is going to react with sodium hydroxide. What is our product here? Okay, so one of the things that you do is you first need to identify the alpha and the beta carbons. So I identify the alpha carbon because it's the one with the halogen. It's right there. And then the beta carbon is the one right next to it. Okay. And so once I do this, right, you need to remove the hydrogen from here and then the halogen from here to form the pi bond. So when we do this, right, that would end up being a carbon with 2 hydrogens left behind, then a carbon with 2 CH3s right there. And so that would be our product. Now, maybe the burning question in your heart is, hey, Dr. Pierce, I see that you only looked at this one right here. Why didn't you go and maybe look at this one over here? You could do either, right? So if you had done that, it would have ended up giving you the same product because this has symmetry. Now, that's not always going to be the case, and we're going to talk about in just a moment if these two were different, which one you would choose. Now, so before we do that, though, we need to talk a little bit more about these alkenes, right? Because these elimination reactions of alkyl halides are going to form alkenes. So it's been a minute since we've talked about their structure, so it would be helpful to review. So alkenes are just, right, hydrocarbons that contain double bonds, right? Each carbon in the double bond is sp2 hybridized, and it has a bond angle of 120 degrees, and these are also trigonal planar. Now, the double bond of an alkene is going to consist of a sigma bond and then a pi bond, which is shown here in blue and here in red. So, the double bond consists of a sigma bond and a pi bond. Now, that sigma bond right here is formed by end-on overlap between the two sp2 hybrid orbitals, right? And it lies in the plane of the molecule. The pi bond here, if you remember, is formed by the side-by-side overlap of the two 2p orbitals, and it's going to lie perpendicular to the plane of the molecule. And that pi bond is what's formed during the elimination. So we can classify alkenes in a couple different ways, and we're going to look at those on the slide. So when we look at our alkene classification, we see here that with these alkenes, there's one R group. And that R group is just carbons and hydrogens, right? And if there's one R group, we say, look, that's a monosubstituted alkene. If there are two R groups, we say that's disubstituted. If there are three R groups, we say that's trisubstituted. And if there are four R groups, we say that is tetrasubstituted. I wanted to show you an example of a monosubstituted here. And I want to remind you, right, that you've got to be kind of good at knowing how many bonds those carbons form. Carbons form 4 bonds. So there's 2 bonds here. So this one has 2 hydrogens. And this one here, that's the R group. And then here is the third hydrogen. When we look at this bond that's disubstituted, we see here that that's one of the carbon R groups, and this is one of the carbon R groups. But don't forget, there's going to be a hydrogen right there and a hydrogen right there. And then when we come over here to look at a trisubstituted alkene, we look for the alkene first, and then we look for the R groups. There's one R group here, there's one here, and there's one here. So that's an example of a trisubstituted alkene. Now, remember, rotation around the double bond is restricted. And so because rotation around the double bond here is restricted, we can end up with cis and trans isomers. And so when we look at cis and trans isomers, I want you to look at these 2 molecules. Right? In these 2 molecules, these 2 groups are different, and these 2 groups are different. And so what we see, but these groups are the same, right? And these groups are the same. And so when we look at this, right, this is a trans isomer because these are on opposite sides. So this would be a trans isomer. And then here, these are on the same side, so that would be a cis isomer. So they're on the same side, cis, that's what I remember. Now, one of the things that I want to point out is that this is shown as cis. And if it's in a U shape, if you have a double bond with a U shape, you automatically recognize that cis. And then if you have a double bond that makes this zigzag shape, automatically you should recognize this as trans. A lot of the bonds that you see in some of your bigger molecules will have these U shapes or kind of these zigzags. And so that's just a really nice way to be able to recognize if it's cis or trans very quickly. Now, these do not interconvert by rotation. They're different molecules. And so we name them different ways. This would be cis-butene. This would be trans-butene. We're going to talk more about where this 2-ene comes from. It's just telling us where the double bond is in another chapter. But the thing I want you to pick up here is that the cis and the trans are out front. And cis means those groups are on the same side and of the double bond. And trans means those groups are on opposite sides of the double bond. Now, these groups have different stabilities. So in general, right, the trans alkenes here, right, are more stable than the cis alkenes shown here because these guys have steric hindrance. And so that steric hindrance is going to destabilize that cis isomer. And so that steric hindrance is lacking in the trans isomer, and so those CH3 groups are farther away. Now, we can also see that the number of R groups increases the stability as well. And so the least stable double bond is going to be the one where we have 2 hydrogens. As we add an R group, then we have more stability. Right? 2 R groups, more stability. And whether you add those 2 R groups to the same carbon or to different carbons, it doesn't affect the stability very much. So we say, hey, look, that's about equal. Then this is 3 R groups, and then this is the most stable with 4 R groups. This is going to help us decide where the double bond forms when you have 2 beta hydrogens to choose from. And we are going to look at that in another screencast, but I do want you to know why that's important right now. So I want you to look at this example where we have but1-ene that's monosubstituted. It's not quite as stable as the cis disubstituted, and then the trans disubstituted is more stable than the cis. So when we look here at the monosubstituted and we come over here to look at this group here, which can be cis or trans, the cis is less stable, and then the trans comes next before we get to the tri-substituted and the tetra-substituted. Now, maybe the burning question in your heart is, why do R groups make the alkene more stable? Well, when we think about this, right, the higher the percent S character, the more readily the atom will accept electron density, right? So what that means then is sp2 carbons are more able to accept electron density, and those sp3 carbons are more able to donate electron density. So remember, the sp2 carbons are what make up the carbons around that double bond. So this means that increasing the number of electron donating groups on the carbon atom able to accept electron density, right, makes the alkene more stable. So that ends this screencast. In the next screencast, we are going to talk about the mechanism of elimination reactions. As always, if you have any questions, please feel free to reach out, stop by my office, or send me an email.